Good day, everybody. Welcome back. Hope you enjoyed your 3 weeks off or whatever it's been. So we're going to finish up the unit today. Actually, we're scheduled to have the last lesson on Friday of last week, I believe. Snow day happened or something, or work day, something. But regardless, we're a little behind. So what I'm going to do is I'm going to extend the due dates for any upcoming homework. So the old one that was assigned before the break is due Monday now. And the one I'm about to assign today is also going to be due on Monday. So your job today and tomorrow is to wrap up any old homework and any old units. And then we will also start to review for a test starting tomorrow also. And then I'll give you a review packet. We'll do that on Tuesday of next week. So you got a test on Tuesday. Between now and then, we're going to get all cleaned up and ready to go. All right, let's go ahead and do our warm-up real quick. Last time we were talking about simplifying roots. So that's exactly what we're going to do right here for our warm-up. All right, here we go. This is a big skill all over your test. So let's make sure we have this kind of thing figured out. So number one is a fourth root. That means you're looking for things raised to the fourth power that go into these. So you better have that table out. You know, that table we've been referring to a lot of times. Things that are raised to the fourth power. Anybody can find anything raised to the fourth power that might go into 64. Maybe 64 itself is something raised to the fourth power. I don't think it is, though. I do see a number on there, something to the fourth power that does go into the 16. A 16 on there. 16 does go into 64. So we're going to break this up into a 16, and it turns out that 16 times 4 is 64. So that takes a little bit of hunting right there. You got to go down your list. You got to check which ones might go into it. Turns out 16 does. Okay, so we're going to write this as a 16 times a 4, because 16 is something to the fourth power. The A is already raised to the fourth, and the B is already raised to the fourth. So there's really not much thought to go with that one. So we're just going to simplify these each one by one and see what happens. Now, according to your table, the fourth root of 16, 16 is 2 to the fourth. Is that what your table says? So the fourth root of 2 to the fourth would just be 2. So the fourth root of 16 right there is the 2 part. Now, unfortunately, there's still this 4 into the root, correct? Haven't dealt with that. And there is nothing to the fourth power that goes into 4, so that's kind of a leftover category. So we have a fourth root of 4 just hanging out as a remainder right there. So the 4 turned out to be our remainder, and the fourth root of 16 turned out to be nice and clean. It turned out to be 2. All right, and as you go down the line, well, here's some variables. And remember what the trick is with your exponent. You take the exponent divided by the root, correct? And for this one, 4 divided by 4 is 1, right? So you get a to the first. And same with the b. You'd have a b to the first. But remember, when you take an even root, your things might need to be in absolute values. And this time, a and b both could be negative. They're not squared. They're not raised to the fourth. They're not always positive. So I should put them in absolute values. And we're all done with that. So hunting for things to the fourth power that go into it, basically. Don't forget your absolute values on even roots. Any questions over that one? Okay. Now, number 2, here it is on the board too. It's got some weird root thingies. 8 root 5 minus square root of 45 minus square root of 80. Whenever you have problems like this, you're just simplifying again, each of them individually, and hope maybe they have something in common that you can work out. So let's get to work. Here we go. Square root of 5. You look down your squares. Does anything go into 5? The answer is no. So we can't do much with that. So we have an 8 square root of 5 here. What about 45? How many squares go into 45? If you look down your list of squares, I believe 9 is on there, correct? And 9 is a perfect square. It goes into 45. 9 goes into it 5 times, right? So I can think of this as a 9 times 5. And we'll do the same kind of thing for the 80. If you go down your list of 80, there is 16 on your perfect squares, and 16 does go into 80, it turns out. It goes into it 5 times. And you can see what's happening in a problem like this. A lot of the terms are going to have 5s left over under the roots. And let's see what else is here. So we got 8 root 5s from the first one. The second one, there was a 9 that went into it. And the square root of 9 is pretty, right? It's just 3. So you have a 3 and a leftover of a 5 under a root. That doesn't help us any. And same with the last one. You have a square root of 16 and a square root of 5. The square root of 16 is just 4. And again, we have a leftover of square root of 5. And now you see that they are actually like terms. We can add and subtract like terms. So you have to do a little bit of work, but it turns out these are all radical 5 things. So if I have 8 things minus 3 things minus 4 more things, well, 8 minus 3 is 5, right? And 5 minus 4 is 1. So I have one thing, or just one radical 5. So my answer for that one is radical 5. All right, let's keep it going. Number 3, got some roots times some other roots. That's kind of weird. All right, this highlights another strategy that was talked last time. If you look at this and you try to simplify them separately, well, no squares going to 3, right? These are exponents of 1. They don't divide by 2. Same kind of problem over here. Square of 24 at I don't know if anything goes into that. One strategy might be to put them back together into a single root and see what happens. Now, I have a 6 and a 4. Those have nothing to do with the root, so we can put those together right now. 6 times 4 is 24. So if you have numbers times, and don't freak out about those. They're just hanging out for the ride, and they just come along. Okay, 24. Let's put all this stuff together back under the root and see if anything cleans up. So we can put these 3ab's and this 24ab cubed. They were both under a root, and since they're multiplied, you can put them back together into 1. Let's see if that helps any. I don't know. Well, what's under this root now? Let's clean things up a little bit. I got 3 times 24. I can figure out what that is with a calculator. 3 times 24, I believe, is 72. And then you have altogether 2 a's, so there's an a squared. And you have 4 b's, so a b to the 4th. And if I look at it now, well, let's see about this thing. This looks like it could be easier to clean up than these were individually. That's kind of the point of putting them back together. If you get desperate and you're not sure what to do, maybe put them back together, see what it looks like as a single thing. Well, 72, I do think there's a perfect square that goes into that. 36 goes into that. If you look up your perfect squares, 36 is 6 squared. 36 times 2 is, in fact, 72. A squared is already something squared, and b to the 4th, if you use your quick trick real quick, what squared is b to the 4th? Well, 4 divided by 2 is 2, right? So you could think of it as a b squared right there. And now, let's just clean up things we got. We got a 24 just hanging out. Oh, square root of 36, that's pretty. Square root of 36 is just 6, correct? Let's see here. What about this 2? Well, that's just leftover, right? Can't do anything with that. Doesn't go anything, right? So there's going to be a square root of 2 remaining. Let's see. Nope, there's the square root of a squared. So they kind of cancel, right? But don't forget, this is an even root, so I need it in absolute values right there. So I have an absolute value of a. And then lastly, you got a b squared squared. So the square root and the square cancel, leaving you with just b squared, which does not need to be in absolute values because it's squared. And whenever you raise something to an even power, it's automatically a positive right there. So it took some work. And there's one more thing you could do. You could figure out what 24 times 6 is. Don't ever leave just 2 numbers multiplied together like that. That's kind of annoying. What is that? 144? So I have a 144 and some other junk left over. Absolute value of a b squared, a square root of 2, kind of chilling right there. It took some work, but we got there. Lastly, number 4. This is something we kind of ran out of time on the last lesson. We didn't get a chance to talk about it, so now is the time to talk about it. Number 4 has a weird root stuff on top and weird root stuff on bottom. And your job is to rationalize the denominator. By that, we did touch on that vocab. We didn't get into all the details. Rationalize the denominator means you don't want any weird stuff in the bottom. See that bottom right there? It's kind of weird, isn't it? Square root of 3 plus 6. You don't want roots in the bottom. So here's your lesson on how to deal with something like this on the bottom. Ready? You multiply the top and bottom by the conjugate of the bottom. It's just like it was with imaginary numbers. So if you were dividing by an imaginary number, you would multiply the top and bottom by the conjugate, and this is no different. This has a conjugate. Conjugate means the same thing, just with the sign in between them change. That's what conjugate means. So you multiply the top and bottom by this thing's conjugate, square root of 3 minus 6. This is very important right here. I'm going to give you a couple of these on your test. It's very simple as long as you know that that's the strategy. So make sure you're understanding the lesson right now. Conjugate. That's how you get out of the woods. Conjugate, conjugate, conjugate. Okay. On the top, it's going to suck. We're going to have to distribute all this stuff out and see what happens. Thank you. Let's see what we get. 9 times square root of 3. Nothing you can do with that. You have 9 times square root of 3. 9 times negative 6 is negative 54. Next, anybody know what this times this is? You should know what square root of 3 times square root of 3 is by definition. Anybody know what square root of 3 times square root of 3 is? It is 3. Yep, square root of 3 times square root of 3 is 3. And 3 times 2 is 6. So there's a negative 6 there. And the last two, negative times a negative is a positive. I know what 2 times 6 is. And I have a weird square root of 3 still chilling. So that top is gross. And that's expected. Just like with complex numbers. When you did with complex numbers, usually the top got pretty disgusting, but the bottom was clean. And this will be no different. When you strip out this bottom, you're going to see why this conjugate stuff works. It's going to make the bottom all nice and pretty. And we'll see what happens when we do this. Well, square root of 3 times square root of 3, as we just said, is 3. Square root of 3 times negative 6 is negative 6 square roots of 3. But here's why the conjugate works. Just like with imaginary stuff, the very next one is going to be a positive 6 square root of 3. And you know that those two are going to cancel out. That's why conjugates work. And lastly, you have a 6 times a negative 6, which is a negative 36. So that's the magic of the conjugate right there. That bottom is now nice and pretty. It has no weird roots in it, and that's the point. Of course, there's slight more cleaning to do. Let's see what happens on top. I have 9 root 3s plus 12 root 3s. That's a grand total of 21 root 3s. On top, I also see a negative 54 minus 6. That's negative 60. And down the bottom, the only thing that remains is a 3 minus 36, which is negative 33. So that's a lot better. And that's the point of this kind of problems. See how the bottom has no longer got weird roots in it? That's the point. Okay, so that's the little mini lesson right there about conjugates. Now we could clean this up just a tad because I think all these numbers have 3 that go into them. 3 goes into this, right? And 3 goes into that, and 3 goes into that. So let's divide everything by 3 because the nerd in me just can't leave it like that. I just got to divide by 3. So I'm going to divide everything by 3. 21 somethings divided by 3 would be 7 somethings. 60 divided by 3 would be 20. And 33 divided by 3 would be 11. So there's a better answer, slightly more simplified. But that's the idea of the conjugate. Did you see the conjugate? Are we okay on that idea? Okay. There'll be one or so like that on your test, so I'll make sure you understand that concept and see it right there, but don't forget it. You see that thing? That's what you got to do. You got to do the conjugate. All right, let's do some LGs. I'm going to try and go relatively quickly through this and give you a little work time. Nonetheless, we do have some vocab and stuff to learn. Pretty straightforward, actually, today. Last section of this unit is about solving radical equations. So we've talked about graphs of radical things. We've practiced simplifying radicals to death. But how do you actually use them to solve equations? If they're in an equation, how do you solve it? It's actually pretty straightforward. Yes, you may. Yes, you may. You guys probably like some shortened homework, would you agree? Yeah? Okay. I think that's fair under the circumstances. Thank you. All right, you want to shorten homework? Okay. Well, I'll make you a deal then. How about the next homework's entirely online, and I only make it like 5 or 10 problems. Is that fair? Okay. All right. That's what I'll do then. So actually, forget this entirely. Okay. It says 6.6. Don't write that down. Okay. Everybody listening here, or listen to me recording this. This is good. Write down that you have to do homework 6.6, but online. Don't write down 3 through 42 or anything like that. I will specifically handpick problems. As soon as class is over, I will make something. I will post it, and we'll make that due Monday. Okay. So both of these, 6.5 and this new one, 6.6, due dates are irrelevant at this point. Everything is going to be due on Monday. Are we clear? Monday, Monday, Monday. Both those due Monday, and 6.6 will not be problems 3 through 42. Not be those. It'll be just 5 or 10 I hand select from online. Cool? All right. Let's get to the business now. 6.6. Last section of the unit. Here we go. It's entitled Solving Radical Equations. Oh, yeah. All right, here we go. So obviously a radical equation is just an equation with a radical in it. So it's got a square root or a third root or fifth root or something like that. You might want to write down step 1 at least. And the process to solve these equations is get a radical by itself. Get the root by itself. That's like my one sentence. Every lesson I have like a 1 sentence breakdown for it. Here's this one. Get the root by itself. Step 2 is just saying, well, how do you undo a root with an exponent? So if you have a square root, you would undo it with a square. If you had a cubic root, you'd undo it by cubing things. If you had a fourth root, you'd undo it with the fourth power, etc., etc., etc. And then you solve it like normal. But please write down this bottom box. That's a big term. Extraneous solutions. When you square both sides of an equation, or you cube both sides of an equation, you might accidentally create answers that weren't there. I won't bore you with the theory of this, but it is possible that when you square something or cube it, you add extra answers. So some of the answers might not work that you do get. And extraneous solution is a fancy word for a solution you got. You didn't do anything wrong, but your algebra somewhere along the way did square or cube to solve it and introduce some extra answers that don't work. So extraneous solution is a fancy word for a solution that doesn't work. Doesn't work. Which means you need to go check these. You need to plug them back into the original equation, make sure they actually do work. And if something doesn't work, you throw it away because it's an extraneous solution. That's basically it. Get the root by itself, undo the root, and check your answers when you're done. That's the whole concept right here. So let's see one. Here we go. Write this one down. Square root of 3x minus 5. There's your root. Your first step will get this all by itself every single time. Get the root by itself. And we're going to see what happens when we do that. So let's get the root by itself. The root's not by itself because we got this plus 2, correct? So let's move the 2 over real fast. We'll subtract 2. Do whatever you got to do. Maybe the right side's just 3. Maybe it's something really complex. I don't care. As long as the root is by itself, we are good. So far, so good. All right. And how do you undo a root? Well, this is a square root, correct? Which by definition, the opposite of a square root is squaring. So as soon as you get the root by itself, you undo it with the appropriate exponent. So if we had this was a square root, so we're squaring. If it had been a cube root, we'd cube. Yes. I don't know. I'm an idiot, aren't I? What? How did I get 3? How about 4? Don't give me the benefit of doubt on that one. That was terrible. That was terrible. That was something I would mock you guys for all day long. I go, oh, 6 minus 2 is not 3, idiot. And then I go do it. So, good catch. Thank you for that correction. Yeah, 4. Better? Okay. Sorry about that. Woo. Okay. So we square both sides. Now, by design on the left, the square root and the square cancel. That's the whole strategy right there, okay? That's the theory. You get the root by itself and you undo it with the power. You got no more root. That's the point. You got no more root, then you're just going to solve it like normal after that. This side is 16 because 4 squared is 16. And then you solve it like normal. So rinky-dink linear, I think I just add 5, divide by 3, and my answer potentially is 7. Again, do not assume that your answer is correct. Okay, it could be wrong, could be extraneous. We got to go back and check it. How do you check it? You actually plug it in and see if it works. So let's plug 7 in. What's 3 times 7? It's 21, right? And 21 minus 5 is 16, correct? And the square root of 16 is 4. And 4 plus 2 does equal 6. So we are good. So 7 isn't officially an answer, but you do need to go back and check. Not every single time is it going to be nice and pretty like that. So watch out for that. All right, let's try this one right here. It looks kind of interesting. It's got a 1/3 power. What does that mean, a 1/3 power? What kind of root is that? It's a root. It's a third root. Yeah. So be careful. You might write it different ways. You like the root symbol, write it with the root symbol. I think probably you're more comfortable writing as a cube root than a 1/3 power. Would you agree? So either way. All right, let's see if I can add this time. Well, here's our equation. Check. Write it down. Change the cubic root into a third power into a cubic root. And again, first step is get the root by itself. So this 9, we're going to add over. 3 plus 9 is 12, right? Just making sure I'm back in school. So let's see, we got a 4 times this root still. Now, is the root by itself? Not quite. There's a 4 in front, right? Well, let's get rid of the 4. The 4 is attached to it. It's times it, right? So let's divide both sides by 4. So we're going to divide both sides by 4. And 12 divided by 4 is 3. Check. Okay, so now that you got the root by itself, we're going to undo it. Now, this is a cubic root. So this time to undo the cubic root, we're going to cube both sides. Make sure you do it to both. And over on the left, of course, the cube and the cubic root cancel. That's why you're doing this. And you're left with 2x plus 6 equals whatever 3 cubed is. If you look that up in your table, that turns out to be 27. So there you go. And then you have the woods. No more roots. Move things around. Subtract the 6. Divide by 2. And you get 21 halves, as weird as that is right there. Now, of course, you need to go back and check it. That's unfortunate. You might want to use your calculator on these, unless you're really good at the mental math. I'm going to try to do it mentally, but I advise you to do it with your calculator, okay? I'll walk it through mentally. 21 halves. You plug in here. Anybody know what 2 times 21 halves is? Well, the 2 and the divide by 2 cancel. So this just turns into 21, and 21 plus 6 is 27. The cubic root of 27 is 3. 3 times 4 is 12, and 12 minus 9 is 3. So it worked out, actually, but that's a lot of mental stuff. I would definitely use my calculator, check things, because mental math is pretty tough, too. Yeah, it's no good. No good. All right, they get a little bit trickier, but that's the fundamental idea over and over and over again. Definitely want to write down this example. This is probably the trickiest ones that will come up right here. It's tricky because it has 2 roots. And these take some patience. Nonetheless, the strategy is the same. Get a root, any root by itself. Is one of the roots already by itself? Yeah, okay. So we're going to undo that root. This is a square root, so we're going to square, right? Now, here's the tricky part, which sucks. If you square this side, you have to square this entire side. You cannot just square the terms individually. Squaring one side, you got to square the whole other side. Now, this kind of helps and it kind of hurts a little bit. On this side, it gets rid of the root. That's sweet. But over on the other side, don't be lazy. Don't be killing puppies. You can't just square these separately. You have to multiply this by itself. That's what it means to square a binomial with 2 things. You have to write it times itself. You have to FOIL it out, and you have to see what happens. Do not be lazy. Number one thing I tell kids all the time is don't just square them separately. What they go do, they just go square them separately. It ain't going to work. You have to do it like this. Which means you have to do some distributing. Well, that's okay. Now, 3 times 3 is 9. 3 times this weird root is 3 times the root. Move on to the next term. The negative root x times 3 is another negative 3 root x. And the last one's a negative times a negative is a positive. And you should know conceptually that the square root of anything times itself is just this thing, right? Square root of 4 times square root of 4 is 4. Square root of 9 times square root of 9 is 9. Square root of x times square root of x is x. So we got this thing. It doesn't seem like it's helping any. It's like, oh, man, I only had 2 roots before, and now I still got 2 roots. Well, it actually does clean up some. First off, I see an x on both sides. See an x on both sides? Let's subtract x from both sides and have it be gone. So that's just gone now. Subtract x. And actually over here, these are like terms. I've got negative 3 roots and negative 3 roots. That's a grand total of negative 6 roots. Now, the reason these ones suck so much is because when you square both sides, this side got ugly and it took some work, didn't it? And it's still got a root in it, doesn't it? But we're better. Now it's only got 1 root in it. It used to have 2. Our strategy will be the same now, okay? I'm looking at this fresh. How do you solve it? You get this root by itself. So we're going to get this root all by itself and then see what happens after that. Well, let's start getting this root by itself. Let's subtract 9. 21 minus 9 is 12. And the root's not quite by itself yet because it's times it's negative 6. So we'll divide both sides by negative 6. And you get the square root of x is negative 2. That's not good. Okay, how are you going to do the square root? Square both sides, right? So on the left, if you square negative 2 times negative 2 is 4, right? And on this side, by design, when you square it, you get x. So take a minute and study that one, because those are the trickiest ones that could possibly come up. Ones that have 2 roots in them, that's the worst. What do? You still get 1 root by itself and square it, correct? The other side squared is going to be a mess. You got to distribute it out, but eventually it'll have a root in it still, right? And you get that root by itself, and you solve from there. Of course, we got to go back and check for extraneous solutions. Let's see, does 4 work? Well, I'm going to go back to the original equation. Here's what we had originally. Let's see what happens when we plug in 4, right? 4 plus 21 is 25, right? And the square of 25 is 5. So this side's 5 when I plug in 4. On the other hand, the square root of 4 is 2, right? And 3 minus 2 is 1. So does 5 equal 1? No, this does not work out, does it? And that's the only answer I had, correct? Well, it doesn't work then. So for this particular problem, there is no solution. That's what you got. That's why you got to go back and check right there. Because sometimes they work and sometimes they don't, which is quite unfortunate. All right, try this one. Write it down. We're zipping right along. It's as bad as it gets right there, 2 roots. Yes, you may. Anytime you see just 1 root, I just see 1 root. You see 1 root? I see 1 root. I see an 8th root. It's not going to be that bad. It's really only the ones where you have like 2 roots that are really going to suck. So first thing I'm going to do, transform that root, that exponent into a root. That's a 6th root, correct? All right. So we're going to recognize that 6th power as a 6th root. And now we're going to get to work. Same strategy as before. Same thing over and over and over again. Let's get, there's a root we're going to get by itself. So let's subtract 8 over. That will give me a 2 when I do. And yes, this has a fraction, unfortunately. That's too bad. So we're going to have to get rid of a fraction. How do you get rid of multiplying by a fraction? You multiply by its reciprocal. Very good. So let's multiply both sides by 3/2. Why does the reciprocal even work? Because here you got a 3 and a divide by 3, right? Cancels, correct? Here you have a 2 divided by 2. That was also cancel. And over here on the right, well, this 2 and this divide by 2, actually, in this case, cancel. So finally, we're going to have the 6th root of 11x plus 14 is just 3. Okay. Well, we got a 6th root all by itself. We're going to undo it with a 6th power. That's the point. 6th power, 6th power. Boom, gone. And now we've got 11x plus 14. So whatever 3 to the 6th is, I think it's 729. Would somebody check me on that, though? Cool. Okay, 729. Big number. Oh, well. But we'll keep working it. We'll subtract 14 from both sides. That would give me 715. And dividing by 11, boy, I don't know what that is. Anybody got 715 divided by 11? Does it work out clean or not? Ooh, that's nice. All right, so we got an answer. X is 65. But got to go back and check, right? Always got to go back and check these. So this is too much for me to do in my mind. You might want to do it in your calculator. Let's see. Do 11 times 65 and then add 14. What is it? 720. Oh, that's great. 729. Now the 6th root of that, you know where your root button is, right? Go to math. Go down a little bit. That x root thing. 6th root of that. Ew. Ew. Yeah. I bet I know what it is. In fact, it's buried in our work already. If 3 to the 6th is 729, then the 6th root of 729 is 3. Did you get 3? Oh, awesome. Okay, so this whole thing is 3. Now 2/3 of 3, 1/3 of 3 is 1, right? So 2/3 would be 2, and 2 plus 8 equals 10. So it did work out. Our answer of 65 is legitimate in that particular case. All right. Now, any questions over that? Getting the root by itself? Get the root by itself, undo with the exponent. Don't forget to go back and check for extraneous solutions. Cool? All right. Now, the last part, I'm not going to do an example over. It's stupid. It's solving by graphing. Do you remember what you do when you solve by graphing? You set it equal to, and you graph it, right? And see where it crosses the axis. That's the whole darn lesson. I don't think you really need any examples on that. Would you concur? So for this one, for example, I'd move the 9 over. Fair. Subtract 9, set equal to 0. Graph the left side. See where it crosses the axis, right? Write it down. So pretty easy, correct? All right, that's it. I don't want to belabor it because that's the whole point. Fair? All right, so 6-5. Finish that up. That's due on Monday. 6-6. I'm going to sit down right now, literally, and create something online where it's just 5 or 10 problems, getting the gist of what we just talked about. Simple or solving root equations. I'll cut through all the nonsense and make it really easy. Do not do 3 through 42. Do not do the online version I'm about to create right now. Tomorrow, we will begin to review for the test. So tonight, you really need to be cranking out 6-5, maybe even 6-6, because tomorrow, I'm going to give you a big fat review packet, and we'll study Friday and Monday for your test on Tuesday.